Welcome everyone to the second lecture for Module 3. So if you remember in Module 2 we looked at single observations and how they relate to the population. And then in the first lecture in Module 3 we looked at sampling and probability. Now we're going to go one step further and we're going to look at samples and how they relate to the population, in particular with single sample statistical tests. In this lecture we'll talk about the difference between z-scores and z-statistics. So if you remember in Module 2 we calculated z-scores for individuals when we wanted to compare them to the overall population. So what if we had group data rather than individual data? Well, if we had group data, in other words, if we had samples, we would then use what's called z-statistics. So we'll compare the mean of the sample to the overall population. And when we do that, we have to calculate z-statistics. So the other question that we will address in this lecture as well is, what if our distribution of scores is skewed in the population? So in Module 2 we talked about we could go back and we can take those original scores and we can square them or square root them and then recalculate our analysis. But that takes a lot of effort, takes a lot of time. There's a much faster way to do it, and that is through sampling. And so if we sample, we can correct for skewness in the population rather easily, and it doesn't take an extra step, such as going back to the original data and squaring or square rooting the original values. What makes sampling so powerful is the central limit theorem. And the central limit theorem addresses two concerns of research. First is that research or hypothesis testing requires a normal distribution, just like z-scores required a normal distribution. So any parametric statistical test requires a normal distribution. So we need to make sure we're meeting that particular assumption. The second concern that it addresses is that there is a lot of error when it comes to statistical analyses of individuals. That people are very different from each other, they have very different backgrounds, very different experiences. That changes their behavior, changes their responses. And so there's quite a bit of variability among individuals. But if we can somehow reduce that variability among individuals, in other words reduce the error, then we can increase our confidence in the results. So the central limit theorem allows us to address both of those concerns by averaging over multiple observations. If I can average across multiple people, then I can cancel out those differences among those individuals. So those people who may be very high on a personality trait, let's say extroversion, would cancel out with those who happen to be very low on the trait of extroversion. And so we're left with less error or less individual differences. So statistically we end up treating everyone as if they're the same. Even though we know there's variability there, for our analysis we'll treat them as if they're very similar to each other. So the central limit theorem allows us to address both those concerns about normal distribution or normality, and also about the amount of error that is when we measure individuals and the variability among individuals and how much they differ from each other. The central limit theorem itself is based on the idea of repeatedly sampling means from the population. So instead of looking at individual scores, we'll take groups of individuals in the population and we'll calculate a mean or an average for that group, and then we'll continue to do that over and over again to create a new distribution, a distribution made up of averages or made up of means rather than of individual scores. So when we say repeated sampling of means, what we're saying is we're creating a new population distribution that's made up of averages of groups rather than individual scores. Now when we do this, when we repeatedly sample from the population in groups and then use the means to create a new distribution, we end up creating a normal distribution even if our underlying distribution is skewed. So if we have a skewed distribution and we repeatedly sample averages or repeatedly sample groups, then we will create a normal distribution out of that skewed distribution. At the same time, like I mentioned before, that if we take groups and we take the average of groups rather than individuals, then we're able to cancel out the individual differences among those people in the group. So we're able to average out the error. This reduces variability in the population. Now, as we talked about before, if we reduce variability, we increase reliability, and we give ourselves the best chance for having higher validity for when we conduct our statistical analyses. When we repeatedly sample from the population and then plot those means in a frequency polygon, we create a new distribution, specifically a distribution of means. In other words, a distribution of averages. So when we repeatedly sample from the population, so let's say we take samples of 5 people from the population, we get the average of those 5 people and then replot it into a new distribution. So we take 5 people, we randomly select 5 people from the population, we get their mean, we plot it, we put those people back in the population, we resample and get 5 more individuals, take their mean, we plot that, we put those 5 people back in the population, resample, get 5 more and take their mean, and as we go through this iterative process we create a new distribution called the distribution of means, or in other words the distribution of averages. We're going to create a new distribution made up of averages rather than of individual scores. So in Module 2 we learned about the distribution of scores, the normal distribution of scores, and so here in Module 3 we're going to learn about the normal distribution of means, in other words the normal distribution of averages. So if you think about those two terms, scores and means, we're really saying with a distribution of scores we have a distribution of individual values, whereas with a distribution of means we have a distribution of averages. So think scores as individual values and means as averages. We can also say on a distribution of score that the sample size is technically a sample size of 1, or n equals 1. When we have a distribution of means, our sample sizes are greater than 1. So in other words, it's not just one value or one individual score, it's multiple scores that are averaged. And so when we talk about distribution of means, that means the distribution is made up of averages, made up of sample sizes greater than 1, so 2 or more. So here is a graphical demonstration of a distribution of means and a distribution of scores, and so this is in your textbook. So if you look at the x-axis, it looks like we have a height in inches of people in general, and of course the y-axis is frequency. And so we can see here on a distribution of scores, that's the orange line here, that it's a normal distribution, but it's made up of individual values. So in other words, each person's height. And then if we look at the distribution of means, that's the blue line, we'll see that distribution of means is made up of averages. So it's made up of several people, and we take the average of their heights as a group, and we plot the group averages rather than the individual scores. And when we do that, the variability decreases. And we can see that here in the graph, that the distribution of means, that distribution is quite a bit thinner than the distribution of scores, which seems to be more stretched out. And that's because we've reduced the variability, we've reduced the error in the distribution by taking averages. And so a distribution of means is going to be narrower than a distribution of scores. It's also less likely to be skewed, because when we take averages, we average out those extreme scores that make a distribution skewed, and that normalizes the distribution. When we create a distribution based on repeatedly sampling means in the population, we create this new distribution of means that will have the same average or the same mean as the distribution of scores. And so the average or the mean of this new distribution won't change, it won't fluctuate much, it'll be about the same. However, this new distribution will have less variability. So in other words, it'll be more reliable, and because it's more reliable, it will give us a better chance for validity when it comes to measuring whatever construct we're measuring. So the other thing that it does for us is that if we have a sample size of 30 or more, that distribution of means will almost always be normal, regardless of how skewed the original distribution of scores is. So if our individual values are skewed, we have a positive or negatively skewed distribution. If we take samples of 30 or more people at a time and create a new distribution of means, then we will normalize that data set. And so repeatedly sampling becomes a lot easier than going back to the original data and squaring or square rooting the original data. So whenever we can get samples, we prefer to do that. It reduces error, it reduces the variability, and it also normalizes the distribution. So you should note also that the symbols have changed here. So remember that in a distribution of scores, so in Module 2, we calculated a standard deviation, and that was represented by sigma. But on a distribution of means, we're going to calculate the standard error. And so the standard error is just like a standard deviation, except now it's based on a distribution of means. And so you'll notice that in the symbol, that instead of having sigma, it will be now sigma sub m. That sub m demonstrates that it's on a distribution of means. So make sure you know your symbols. Note that if there is a sub m behind a symbol, then that's telling us that it's on a distribution of means. And so the means will stay the same. We'll have less variability. When we have 30 or more observations in a sample and we compare it to the population, that population distribution will almost always be normal. So that addresses our concern about skewness. And then also note that there are symbol changes, that if we put a sub m behind the symbol, we're talking about a distribution of means rather than a distribution of individual scores. CLT here stands for central limit theorem. So the central limit theorem will tell us that when we repeatedly sample from the population and then plot those means into a new distribution, that the new distribution of means will have the same average as the distribution of scores. However, it will also have less variability. We will reduce error, we will reduce individual differences, which will allow us to have higher reliability and give her a better chance for validity. Incidentally, that also helps normalize the distribution. So know what the central limit theorem says, know what it does, and know what concerns it addresses when it comes to research, and particularly the concern about a normal distribution, and then also the concern about variability, or in other words, error. When we sample, the new measure of variability will be the standard error. And so to calculate the standard error, we need to know two things. And so here's a formula. So note we have sigma sub m. That tells us it's the standard error. Technically, it's the standard deviation on distribution of means, but that's too long, so we just call it standard error. We need two things to get that standard error. We need the standard deviation on a distribution of scores, and we need to know the sample size. In other words, the number of observations. So if you see here in the formula, if we know sigma, the standard deviation on a distribution of scores, then we can take that standard deviation and we can divide by the square root of the number of observations in our sample. And if we do that, then we'll get the standard error. Also remember that when we repeatedly sample from the population, that the mean stays the same between the distribution of means and the distribution of scores. And so here we have mu sub m, that tells us the average on a distribution of means. But we'll also note that it still equals the average on a distribution of scores. And so the average won't change, so we will equate it as being the same. So we'll have mu sub m will equal mu, so they stay the same. So the formula is just mu sub m equals mu, the means stay the same between the distribution of means and the distribution of scores. Now whether we use the standard deviation or we use the standard error in our formula will depend on if we're calculating z-scores or if we're calculating z-statistics. So if I want to compare individuals to the population, then I'm getting z-scores. In other words, I'm getting z-scores for individuals or individual scores. Here, n equals 1. The number of observations is each individual. If that is the case, we will use the standard deviation. However, if we're using samples, so anytime we use samples, if we're using samples, then we're calculating z-statistics. And so z-statistics are for groups. This is when our number of observations are greater than 1. So in other words, there's 2 or more. If that is the case, and we're taking averages of these samples to compare to the population, then we're going to use what's called the standard error. So if we're looking at individuals and comparing individuals to population, we're using the standard deviation in our formula, we're using the z-score formula. If we have samples, then we're calculating a standard error, and we're using the z-statistic formula. So here's a formula for a z-statistic. In other words, the formula for a z-test. You'll note that this formula looks very similar to the formula for z-scores. In fact, it's designated by the same symbol, z. But the difference is in the formula itself. You'll notice that instead of x, we have m, and it's the Latin Roman letter m, telling us it's the mean of a sample. And we'll subtract the mean of the population, in other words, mu sub m. The sub m tells us it's on the distribution of means. So when I have a sample, I need to compare it to a population of the same, made up of the same sample sizes, and that's the sub m part of the symbol. And then we'll take that numerator and we'll divide it by the standard error, and remember the standard error is just the standard deviation on a distribution of averages or a distribution of means. So we'll have sigma sub m. So to get a z-statistic, I need to know the population mean, I need to know the population standard error, and I need to know the sample mean. And if I have those, then I can calculate a z-statistic. Once we know about the central limit theorem and what it does, and we also know the formula for a z-statistic, then we're ready to analyze our first hypothesis test. And so I'll have you answer a few questions here, like you normally do in a lecture, and we'll come back to the next segment where we'll walk through the steps of a hypothesis test.